Lab 3 of Physics 2212 at Georgia Tech. My name is Cooper Allen. This is section X21. So just as an introduction to this lab, the purpose was to measure the distance dependence of the magnetic field due to a small bar magnet, and then to compare our measurements in the real world to the distance dependence predicted by equations that we wrote in GlowScript VPython for the on and off axis magnetic fields derived from the Biot-Savart law. So some of the fundamental concepts here, obviously, the Biot-Savart law, which is written here. We also have a relationship for the magnitude of a magnetic dipole based on the distance from it, and that is seen here. And this, which is a derivation of it that gives us a linear form of it, which was useful in our data, as you'll see later. Here we have our mu value, which is one of the main results of this, and also the n value that you can see here. So the experiment, the first step is to locate the magnetometer in your phone. That involves some meter sticks and magnets and aligning things. That wasn't really the main focus of the experiment, it was just kind of a setup thing. Once you have done that, however, the first real thing you do is record the magnetic field of that bar magnet perpendicular to the magnetometer in your cell phone at a given distance. The next step is to move your cell phone that same distance perpendicular to the meter stick. And so it should start out d perp is the distance between the magnet and your phone. Say that's along the x-axis, you then move your phone along the y-axis that same distance. You should now have a 45-degree angle between where your phone used to be in the magnet and where your phone now is in the magnet. And you repeat that with other given values of d perp to find more data. Data that looks like this. That is all of that. Once you've moved your phone, that's this off-axis info. Doing it before you've moved the phone gives you all this info. Here you can see the linearization of that, which is why this formula was important. And this, you can see the slope and the intercept, both of which are useful later on. Just to define the system is the bar magnet, the surroundings are literally everything else. And the initial conditions are your phone is just resting on the meter stick with the magnetometer aligned on the stick so that it is a perfectly straight line between the magnetometer and the bar magnet. This also needs to be aligned so that Earth's magnetic north doesn't have much of an effect. Here is all the code for that. Most of this we were given, although here you can see like our actual measured distance, B scale, which we made just to make the arrows look good, which you'll see in a moment. This equation for actually doing the calculations for the dipole equation from the Biot-Savart law that you see here. And of course all of the where the other vectors should go. Here, even more code. Again, most of this was given to us, or just pretty much fill in the blanks. I did add a little bit extra just so I could have it calculate the magnitude for me, just so I didn't have to. This is what it outputs. So you can see here's the 45-degree angle one, here the one's perpendicular, and here parallel. The magnitude outputs down here. So yeah, our theoretical magnitude, the one computed by GlowScript, was 3.5395 times 10 to the negative fifth Teslas. The experimental one, however, was 4.9490, which has an experimental error of like 39.8%. This could be due to misalignment with the magnet, misalignment with Earth's magnetic field, extraneous ferrous objects in the workplace, a problem with the mobile apps we were using, any number of things. but all in all, it was actually more accurate than I had expected. So finally, what if? What if we hadn't oriented the experiment to compensate for magnetic north? That would have certainly made it more difficult. It would have made the calculations harder, but it wouldn't have made it impossible. It would have taken longer, but it could absolutely be done with accuracy. Is to stick two magnets together, since they're at the same place, and they're identical magnets. All you're really doing here is doubling the magnitude. You're not changing the direction at all. They're not counteracting each other. They are working in tandem to just double the value